All right, so next up we have section 4.4. We've already discussed the inverse properties, exponential properties, and change of base properties of logarithms. So let's go ahead and move on to the new stuff here. We have a sum of logs property. This tells us that log base b of a plus log base b of c is equal to log base b of a times c. In other words, the sum of two logarithms is the logarithm of the products of their arguments. So if I'm adding two logarithms, I can combine it into one logarithm with the same base. Notice that all of these bases are the same by multiplying the arguments of those logarithms inside of this new log. Similarly, I have this difference property. If instead I am subtracting two logarithms, and notice again, same base. This doesn't work if they have different bases. They have to have the same base. If I'm subtracting two logarithms, I can express this as one logarithm, wherein I am dividing these two arguments. And of course, this works both ways, right? I can expand a logarithm in which I have multiplication by breaking up into two logarithms that have a sum between them, right? And similarly, a logarithm with division inside of it, I can express as the difference of two logarithms instead. So let's look at some examples in order to figure out what's going on here and how to use this stuff. Write log base 3 of 5 plus log base 3 of 8 minus log base 3 of 2 as a single logarithm. So the first thing I want to do is let's go ahead and use our sum of logs property on these first two here. Log base 3 of 5 plus log base 3 of 8 is log base 3 of 5 times 8, which is log base 3 of 40. So now I have log base 3 of 40 minus log base 3 of 2. And in order to combine these, I can divide their arguments inside of one logarithm. This is log base 3 of 40 divided by 2, which is log base 3 of 20. That's my answer, log base 3 of 20. I've written this expression as a single logarithm now. Evaluate 2 times log of 5 plus log of 4 without a calculator by first rewriting this as a single logarithm. The first thing I can do is use my exponent property on 2 log of 5. Notice that I'm allowed to bring this 2 inside of the logarithm as an exponent. So this is log of 5 squared, which is log of 25. This turns this problem into log of 25 plus log of 4. And now I can use my sum property to say that this is log of 25 times 4, which is log of 100. And log of 100 is just log of 10 squared. The common logarithm has base 10, so this is log base 10 of 10 squared, which is 2. Rewrite natural log of x to the 4th times y over 7 as a sum or difference of logs. Okay, so the first thing here that I might notice is that I have a quotient of two expressions. So let's break that up using the difference property. Let's say that natural log of x to the 4th y over 7. Let's break up this division by turning this into a difference of two logarithms. It's going to be the difference of the numerator, which is natural log of, or rather it's going to be the natural log of the numerator minus the natural log of the denominator, right? Now, I can further break up this part, this natural log of x to the fourth y. Here, let me use a different color to show that this is a bit of a side note. Natural log of x to the fourth y. This is natural log of x to the fourth plus natural log of y. This is using our sum property. Then this entire expression becomes natural log of x to the fourth plus natural log of y minus natural log of 7. And then I should really, to fully expand this, I should go ahead and use my exponent property on this first term to turn this into 4 times natural log of x plus natural log of y minus natural log of 7. And this is my answer. Let's go back to this chemistry example. Recall that in chemistry, as we did at the end of 4.3, pH is equal to negative log of H+. If the concentration of hydrogen ions in a liquid is doubled, what is the effect on the pH? Okay, let's say that normally C is the original concentration. This means that 2C is the new concentration. Right? So normally, the pH is negative log of C, right? Normally, let's say that the normal pH, P, this is negative log of C, right? This is the normal pH. But our new pH, if I double the concentration, this is going to be negative log of 2 times C. And this is going to be negative. I can break this up using my sum property. Log of 2 plus log of C. And this is negative log of 2 minus log of C. And log of 2 is about 0.301. So this pH is about negative 0.301 minus log of C. Negative log of C was the original concentration P. So this new pH is my original concentration minus 0.301. So when the concentration of hydrogen ions is doubled, the pH decreases by 0.301. Let's look at using some of these log properties in some other math problems. Let's solve log of 2x minus 6 equals 3. Maybe the best way to do this is to exponentiate both sides. So I have 2 to the power of log of 2x minus 3, or 2x minus 6 rather, is equal to 10 to the power of 3. Because my exponential base and my logarithmic base, which implicitly is 10 in the common logarithm, are the same, the left-hand side becomes 2x minus 6. The right-hand side is still 10 to the third power, but 10 to the third power is 1,000. And x is really easy to solve for here. If we add 6 to both sides, I get 1006 on the right-hand side. Dividing both sides by 2 gives me that x is 503. And I want to check for extraneous solutions. So I want to plug 503 into this equation, at least mentally, because I cannot plug a negative number or 0 into a logarithm. That's actually going to be something that we talk about a little bit more in the next section. So if I plug a number into a logarithm and the input is negative or the input is 0, then that thing cannot be a solution. In this case, plugging in 503 looks like it's going to be perfectly fine. Let's look at this problem. In order to solve this one, the first thing that we need to do is get everything inside of one logarithm. I need a single logarithmic expression on this left-hand side. So I can use my difference properties to write this as log of 50x plus 25 divided by x is equal to 2. And now exponentiating both sides gives me 10 to the power of log of 50x plus 25 all over x equals 10 to the power of 2. So I get 50x plus 25 over x is equal to 100. If I multiply both sides by x, I get 50x plus 25 equals 100x. Subtracting 50 or 50x from both sides, I get 25 equals 50x. And when I divide both sides by 50, I get that x is 1/2. And now if I plug 1/2 into my original equation, it doesn't look like I'll have any negative numbers, and it doesn't look like I'll have any zeros on the insides of these logarithms. So this is fine. Next example here. So the first thing that we want to do is use our sum of logarithms property on this left-hand side. If I'm adding two logarithms and they have the same base, then I can combine these into one logarithm, where the operation on the inside is multiplication. The right-hand side is going to remain unchanged for the time being. I need to be very careful and make sure I multiply out the inside here correctly. It's going to be x squared plus x plus 2x, so plus 3x, plus 2. This is equal to natural log of 4x plus 14. The logarithmic base on both sides here is e. So if I exponentiate with this exponential base of e on both sides, my logarithms will cancel, leaving me with x squared plus 3x plus 2 equals 4x plus 14. And now I have to solve this like a normal logarithm. So I'm going to get everything onto one side. I'm going to subtract 4x plus, I'm going to subtract 4x, and I'm going to subtract 14 from both sides to get me x squared minus x minus 12 equals 0. I can now factor this. I need two numbers that multiply to get me negative 12, that add to get negative 1. These numbers are negative 4 and positive 3. And when I solve here, I get x equals 4 or x equals negative 3. I get x equals 4 or x equals negative 3. Now, whenever I check this, in my original problem, x equals 4 looks perfectly fine. I don't get anything negative and I don't get any zeros inside of these logarithms. But x equals -3 is going to cause an issue, because if I plug -3 in, then I start getting a negative from the very first logarithm here, right? Natural log of -3 plus 2 would be -1. So x equals -3 is not a solution. Our only solution here is x equals 4. We say that x equals -3 is extraneous. We call this one extraneous. All right. And let's see. Let's look at this problem here. In 2008, the population of Kenya was approximately 38.8 million and was growing by 2.64% each year, while the population of Sudan was approximately 41.3 million and growing by 2.24% each year. If these trends continue, when will the population of Kenya match that of Sudan? So we're going to start by writing an equation for each population in terms of t, which will be we're going to say t is the number of years after 2008. So I'll call this k of t for Kenya. And this is, the initial population here was 38.8 million. So we're going to write this, we're going to write an equation that'll give us an answer in terms of millions here. Times 1 plus 2.64% is 0.0264 raised to the t power. My other equation will be s of t. This is 41.3 times 1 plus 0.0224 to the t power. If I want to find out when these populations will be equal, I can set them equal to each other and solve for t. So I can say 38.8 times, this is 1.0264 to the t power equals 41.3 times 1 plus, or rather times 1.0224 to the t power. Probably the best way to solve this is to go ahead and get all of the numbers on one side and get all of the exponential stuff on one side. It doesn't matter the order in which you do this or what side you divide by what. I'm going to divide both sides by 38.8 first. So I have 1.0264 to the t power is equal to 41.3 times 1.0224 to the t power all over 38.8. And now I'm going to divide both sides by 1.0224 to the t power. Oh no, I just showed everyone that I have Minecraft installed. I play Minecraft with my wife. It's fun. Anyway, where was I? So at this point, on the left-hand side, I have 1.0264 to the t power over 1.0224 to the t power is equal to, on the right-hand side, this stuff has gone away. So I have 41.3 over 38.8. This is going somewhere. Notice how the top and bottom of the fraction on the left-hand side are raised to the same power. That means I can express that as 1.0264 over 1.0224 raised to the t power This is equal to 41.3 over 38.8. And now let's take a logarithm of both sides. Let's say take the natural log of both sides. Doesn't matter which logarithm I choose. Then I have t times natural log of 1.0264 over 1.0224 is equal to natural log of 41.3 over 38.8. Divide both sides by natural log of 1.0264 over 1.0224 in order to isolate the t. And I get that t is natural log of 41.3 over 38.8 divided by natural log of 1.0264 over 1.0224. And if I type this into a calculator, I get about 15.991 years. All right, not too bad. And that's it for section 4.4.